Dr. Steve Zinkle. Steve is currently Governors Chair at the University of Tennessee in Knoxville. Steve got his PhD in nuclear engineering and material science from the University of Wisconsin-Madison, and he has written more than 250 papers, and is a fellow of the American Physical Society, Materials Research Society, the Minerals, Metals, and Materials Society, and ASM International, the American Ceramic Society. Most importantly, Steve was a lecturer at the summer school in Sicily more than 10 years ago. It's like, it was in 2002, is that right? I was a student and listened to 2 weeks long lectures of Steve and Kurt Zinkle, and Kurt Zinkle, who is now the chair in the Material Science Department in Tennessee, organized it. And it was a fantastic summer school. And for me, at least, it was sort of one of the turning points where I decided that nuclear materials and nuclear energy was interesting. And so it's a pleasure to have Steve here now speaking again, listening to his talk about science basis for design of high-performance radiation-resistant materials in advanced nuclear energy systems.
Okay. Thank you very much, Peter, for that introduction. It's nice to be here at Berkeley. So what I'll be trying to cover today is giving you a brief overview of some of the radiation-induced degradation phenomena in materials that have been irradiated. And that'll be kind of the first half of the talk. And then the second half of the talk is some prospects. Taking that knowledge that we've learned, how do we go forward to develop new high-performance radiation-resistant types of materials? And particularly, there's three general strategies that I'll get into a little bit later. So as an obligatory kind of a slide for just motivating the reason why we're interested in this, which for most of you here in this audience isn't really necessary, there's various correlations that have been established over the years. This is one from the United Nations, quoting what's called a Human Development Index, showing the very strong positive correlation between quality of life, as measured by this Human Development Index in this case, and access to electricity. And the second important motivator for this is, so quality of life is related to access to energy, or in particular electricity. Secondly, energy is big business. So this bottom graph is just showing for different regions in the world, and then the world average, how much we as consumers spend each year for energy as a fraction of the gross domestic products for each region or worldwide. And energy is 10%. It's so important for manufacturing, for essentially everything that we do in life, that it's a very significant fraction of our overall gross domestic product. And it varies a little bit, country to country. Currently in the U.S., because we've got some cheap oil due to fracking and natural gas and so forth, we're falling a bit under that. But historically, it's been about 10% in the U.S. For many years as well. So then we can look at choices for energy. And you can look at it in several ways. So if you look at the current mix in the U.S., about 20% is nuclear. The coal is about 40% and dropping recently. Natural gas is about 25% and increasing recently. And then there's some other renewables and hydropower. And in terms of non-emitting sources of electricity, if we're worried about global warming scenarios, nuclear is about 65% of the non-emitting fraction of electricity. The other factor that one can use is reliability of the source, and so in terms of the nameplate capacity factor, nameplate total maximum electricity production per year versus how much is actually delivered to the grid each year, nuclear is the gold standard for production of electricity. For the last 10 years, it's been averaging 90% of the maximum availability that the reactor shuts down for refueling for on the order of a month to 6 weeks or so to 2 months, then starts up, runs for 1.5 to 2 years, shuts down for 6 weeks or so refueling and maintenance, starts back up and just keeps doing this over and over again. And it makes the local newspapers when the nuclear power plant shuts down anytime during that 1.5 to 2 year period, because it is such an unexpected type of an event. Coal is about 65% availability, and then various other energy sources fall off. Of course, the renewables, solar and wind, are lower because they are intermittent energy sources. Gas could be as high as coal, but it's actually used as peaking. It's something that's easy to turn on and off, so that's, its capacity factor, if you will, is artificially low because it is quickly something that can be turned on and off. But nevertheless, nuclear is dominant in terms of its reliability. If you look at in terms of operating conditions for particularly the structural materials in reactors, this is just a kind of a color-coded cartoon chart indicating in terms of operating temperature and the unit of displacement damage that I'll talk about in a little bit more in the next few slides, called displacements per atom, degree of radiation damage in the material. Where our current experience base is with existing light water reactor technologies, and where the next generation, so-called generation 4 fission reactors would operate. You can see, without going into the details of each individual type, they're generally higher operating temperatures, higher temperatures, both of which cause more severe demands on the material, requiring more high-performance materials compared to our current design-based or operating experience. And then fusion, shown over here, is an even more severe challenge overall in terms of the operating environment. So this unit of displacements per atom, for those of you that aren't familiar with that, one displacement per atom, or DPA, means that every atom has been knocked off of its lattice site. So a unit of 1 is a very large unit, 100% total displacement of atoms from their initial lattice site. And what happens is that many these atoms, when they're knocked off, they'll migrate around in the lattice and they'll hop back into another site that's been, the atom that's been knocked into an interstitial site will migrate around and it'll hop back into a vacant site created by another displacement event, typically. And so you end up getting some self-healing from that. Considering that we want materials that have a very high self-healing and don't have a lot of dimensional instability and so forth, so if we want to reach a damage level on the order of 100 dPa and less than 5% swelling in terms of retained defects in the material, that means you have to have a self-healing fraction on the order of 99.95%. If you take just random materials out of the periodic table, nature gives us about 99% self-healing just off the bat. And so the role as material scientists are getting that extra 0.95%. In terms, that's where the material science comes in to design the radiation resistant materials that have the high performance. So now I'm going to just take a little bit of a detour and talk a little bit about the history of the displacement damage quantification. So these are a few slides that I just threw in kind of late this morning. And so I'll try to just speed through these quickly. But where I'm going is that we've had a unit that I'm going to talk about, this displacement per atom, that was developed in the 1970s, and there's a fair chance that in the next year or two we're going to be going to a new or more broader international standard that will go and build upon this DPA value and go beyond it. So just a little bit of history for this. So in terms of quantifying defect production in materials, Eugene Wigner, back in the early to mid 1940s, was the first one to recognize that for the future success of commercial nuclear power, we had to take account of radiation damage effects in the materials, wrote an influential paper in the mid 1940s. Several people after that developed some quantification of this DPA model, or how to quantify the amount of displacement damage occurring in material. So Frederick Seitz wrote an influential paper talking about the concept of something that's called the displacement threshold energy. A couple years after that, Kinchin and Pease in England wrote a paper that was the first physically accurate model for quantifying displacement events. And then kind of after that, and from the 1950s through the early 1970s, there was a proliferation of different models in different countries for what people were calling DPA. So in England, they developed a further improvement upon the 1950s model that they called the half-Nelson model, after a person named Nelson. There was in France, because they couldn't do the same thing as England, they developed the French DPA. The Americans largely couldn't figure out which they wanted to do, so they generally followed the Kinchin-Pease, the 1950s model. Sometimes, though, we would use the half-Nelson DPA. I don't think we ever used the French DPA, but similarly, the Soviet Union also had a varying thing. So when people talked DPA, nobody knew what it really meant. They were quantitatively different models that were being used. So in the early 1970s, Ian Torrens and Mike Norgett came to Oak Ridge with Mike Robinson, and they sat together and said, okay, we've got the English and French and other models. What really is the right model to use? And they basically came up with the Norgett-Robinson-Torens model, and they developed that over a couple of years after they came together in the early 1970s. And so this was a major improvement about 20 years after the original Kinchin-Pease model, and had a number of physics things that I won't go into detail that improved upon that initial model in the material. So essentially where we are today, it's now 40 years since the NRT model was published. And 2 years after the NRT model was published, there was several papers that showed it was basically quantitatively wrong. And we spent the next 38 years realizing that this is wrong, but that it's still the best thing that we had, and nobody wanted to immediately throw out something that took 20 years for the international community to come together. But we're just embarking on a new international activity that I don't think I've quoted in this slide, but it's a Organization of Economic Cooperation and Development agency has put together an international panel to try to talk about what can we do to go to the next step beyond the current DPA. So essentially, this is a flow chart, logic chart of a sequence of events that happens when you have an initial atom being knocked off its lattice site. A bunch of things happen. You have some initial transient, temporary atomic mixing that occurs in the material. And then you get some additional recovery going on with that. And you eventually, at the end of this process, you end up with some surviving defect fraction at the end of that. So the NRT DPA did a pretty good job of calculating this. It didn't try to even attempt to talk about this rapid interatomic mixing that occurs in displacement cascades. and didn't correctly account for the recombination that occurs within this energetic mixing kind of effect. So the new international standard, if you will, is trying to address this first part. There's lots of other boxes in this chart that I'm not even going to talk about that we've recognized for at least the last 15 years of additional complexities that we should have, but this committee decided that trying to tackle all of this in one fell swoop was going to be too much, but we're going to first start out by getting us at least a little bit further down this logic chart. So going back in history, what the NRT model in the 1970s did compared to the original Kinch and Pease model is shown in this plot of the number of displacements versus recoil energy. It basically corrected for ionization effects in a displacement cascade event, and where in the 1950s it was just computationally too hard to calculate this over the full range of energies. In the 1950s they just assumed that we can just curtail this number of displacements once you get up to really high energies. The NRT model more correctly included the displacements that would occur at very high energies, and then where the Kinch and Pease model over-predicted the number of displacements at intermediate energies, the Kinch and Pease model subtracted away the ionization and took care of things pretty well. So that was a reasonably good model for the 1970s. But again, what it didn't do was look at the transient atomic mixing that occurs within energetic displacement cascades and some of the recombination of the defects that leads you with a net reduced fraction of defects compared to what's actually being produced according to the NRT DPA model. So plotting here some molecular dynamic simulations for different energy displacement cascades. So number of defects being produced as a function of time. So a neutron or some ion comes in, strikes the initial atom, knocks it off its lattice site, and then that atom quickly knocks off an adjoining atom, and you get quickly a rapid buildup of number of defects within a single displacement cascade event that could be tens of thousands of atoms involved in this process. And after a certain period of time that's measured on the order of a picosecond, 10 to the minus 12 seconds, so extremely short period of time, then you start to get some of the defects recombining, and then it eventually comes out after 1 to 10 picoseconds at some final kind of a steady state value of defects. So the defects that remain after this cascade event is about a factor of 50 or so less than the peak number of transiently displaced defects. So why is this important? If you're looking at some things like void swelling or some other traditional radiation effects, it doesn't matter. On the other hand, if you're looking at an ordered compound, then you get a tremendous amount knocking, and if you have an AB alloy and you knock an A atom off its site and it lands on a B atom site, you get what's called disordering, and that can have a huge effect on the properties of that material. So here's just showing an example for an ordered copper-3 gold material. You get an enormous, and these dark regions are where you're getting disordering. So there could be no defects produced, radiation defects, but you've got disordering produced from this event. Similarly, for things like amorphization that can occur in ceramic materials and intermetallic compounds and semiconductors, these white spots here are examples of direct in-cascade amorphization that's occurred. And this will not scale at all with DPA, but it will scale very well with this disordering type of a parameter. So the first step, what's being proposed is a unit that's called replacements per atom that captures this intense atomic mixing that occurs in materials. And this is just a plot, and the dashed purple line is this replacements per atom factor. The solid black line is the NRT DPA value. You can see there's no good correlation between the two of these. And so for processes that are dependent on this transient atomic mixing parameter, we never should have been using DPA, and now we'll have this new unit called RPA, replacements per atom, that will be the appropriate unit to use for some of these mixing types of parameters. Then the second major effect is after this peak transient displacements, there's additional recombination that occurs and ends up giving you a much smaller fraction of retained defects compared to what is calculated by the NRT DPA. The physics for this is that there is a spontaneous recombination radius between a vacancy and an interstitial that's on the order of 2 to 5 lattice parameter spacings. And in a energetic displacement cascade, you create a lot of defects in a very small volume, and so many of those will recombine with one another and leaving you with a net smaller concentration of defects than what the simple binary collision approximation NRT model would have predicted. So if we just look at some experimental data that have been generated over the years, looking at the defect production efficiency, which is normalized to the NRT DPA fraction, as a function of the damage energy, the energy in the displacement cascade, you start with values that are near 1. It actually goes above 1 at very low energies, which is another artifact of the NRT DPA model I won't get into right now. But as you go to higher and higher energies, you get, relative to the calculated NRT DPA value, you get less and less surviving defects until it finally starts to plateau at something on the order of 30% of the NRT calculated DPA value. So in short terms, at high energies that are relevant for fission neutron and fusion neutron irradiations, the NRT DPA calculation is about a factor of 3 off or wrong compared to what actually does survive in these displacement cascade events. So what's happening at this region where you get this plateau is you begin to form what are subcascades in the material, where you, instead of just forming one ever larger displacement cascade defect cluster, the cascade breaks into some smaller lobes. They're called subcascades. And so here's a plot showing the number of subcascades that are visible by transmission electron microscopy as a function of this initial energy that's produced from a displacement event. And so above a certain critical value, you start to produce multiple subcascades in the material. So as a net result of all of this, I'm plotting here in black, again, the NRT DPA. This is a plot of surviving number of defects versus initial primary knock-on atom energy or damage energy. And again, in the purple dashed region is the new parameter. In this case, we're calling this the arc DPA, which is a mouthful. It's athermal recombination corrected DPA. So even no matter what temperature you irradiate the material, you'll always get this amount of recovery of the displacement surviving defect fraction relative to the original DPA. And this ends up being on the order of a factor of 3 correction at high temperatures and smaller corrections at the lower temperatures. So again, this is in this OECD NEA report that I think is within a week of being officially publicly distributed. It's going through the final editing at the OECD NEA office in Paris. Okay, so that was the 10-minute or so diversion, just to kind of get you up to date on where we are in terms of quantifying amount of displacement events or processes in materials. So now back to the main activity topic for this seminar. An important point to consider when trying to design radiation-resistant material is what is the temperature that the material will want to be used. And you can scale the types of microstructures or the response materials to irradiation into different temperature regimes shown here. So this is a collage of different images I've taken over the years of different materials irradiated at different temperatures, and I've normalized everything here to the melting temperature as kind of a first order parameter that's related to many of the other important point defect vacancy migration energies, interstitial migration energies, and so forth. That to first order normalizing things to melting temperatures is a useful scaling parameter. So what happens at low temperatures, you get one type of microstructures. Without going into the details, at medium temperatures, you get dramatically different types of microstructures, and at high temperatures, you get yet another dramatically different types of microstructures. And again, to a large extent, you can scale this according to melting temperature of the material. But these different microstructures then drive a host of different types of physical responses of the material to the irradiation. And in general, at very low temperatures, particularly if it's a ceramic or near metallic, is a region that should be avoided at all costs. That you will tend to get very poor radiation response for nearly any material at low temperatures, where low is defined as the onset temperature for interstitial migration in the material. And that's often at something on the order of 1/20th of the melting temperature of the material. So it's usually at very low temperatures, 50 Kelvin or something like that, maybe 100 Kelvin in many types of materials. Then you have a broad region between the onset temperature for interstitial migration and the onset temperature for vacancy migration, which are called in the literature as stage 1 and stage 3 temperatures, where essentially any material has wonderful radiation response. And I'll get into that a little bit more later. And then if you go, so that's a great region to operate your any material. And then as you go to higher temperatures, you get into a really diverse set of microstructures occurring in material, which in turn give rise to void swelling, give rise to precipitate instabilities, all kinds of things that happen. This is arguably the most challenging regime to try to design radiation-resistant materials, but we have several potential tools available to come up with radiation resistance that I'll talk about in just a few minutes. So you can kind of then take that information from the previous slide and just list 5 key radiation damage degradation phenomenon shown in this chart, which are listed roughly in terms of increasing temperature, going from low temperatures to high temperatures. So at low temperatures, it's radiation hardening and embrittlement. At high temperatures, for a structural material, it's usually defined by thermal creep. And in the case of neutron irradiation, an additional consideration is something that's called high temperature helium embrittlement, where you get helium being produced from nuclear transmutations with the interactions of the structural material with neutrons, generating helium. And at high temperatures and with applied stress, that helium can migrate to grain boundaries and produce very large cavities on the grain boundaries. You can imagine that this grain boundary with these cavities would be very weak, so you'd have a very poor performing structural material at those high temperatures. So this first and last phenomenon generally define a temperature window over which you might be able to operate typical structural materials. And then the middle 3 phenomenon will tend to define a maximum dose or operating a lifetime that you can operate the material. And the 3 intermediate temperature phenomenon are phase instabilities, which can be particularly profound in certain classes of alloys and less pronounced in others. Irradiation creep, which acts in addition to normal thermal creep, but it extends down to much lower temperatures than normal thermal creep. and finally volumetric void swelling in materials. Just to go through one example of those 5 categories for the radiation hardening and loss of elongation phenomenon, so which happens at low temperatures. So what's the consequence of the radiation hardening? Well, you get increased strength, which is great. You've got the materials become stronger for free. So if that was the only consequence, then that would be a great benefit. But of course, along with that increase in strength, there are negatives. In particular, you get, in essentially all cases, a decrease in the tensile elongation of the material that might cause you to have to adopt more conservative structural design criteria rules for the materials, for the structural material, particularly if the uniform elongation goes less than 2%. And for BCC, body center cubic types of metals, also you can have an increase in the ductile to brittle transition temperature and a decrease in the upper shelf toughness of that, which could be a catastrophic kind of an event to be avoided. So if you look at the typical effects of irradiation on the tensile properties of this is a body center cubic material, but a face center cubic material would show similar types of results, showing in green the unirradiated curve, yield strength versus radiation temperature. And as you begin to irradiate the material, 0.1 dPa, half a dPa, several dPa, at low temperatures you get this pronounced increase in the strength of the material. And then above a material specific characteristic critical temperature, you get a pronounced reduction in the amount of radiation hardening, where it starts to come back and approaching the unirradiated value at the higher temperatures. And this critical temperature is often on the order of about 1/3 of the melting temperature of the material. So again, this increase in strength is wonderful, but unfortunately it brings along with it the decrease in the uniform elongation in the material. So even after a tenth of a dPa or half a dPa, you can see uniform elongation values that are now approaching 0 up to that critical temperature, on the order of 3/10 or so of the melting temperature. If you look at the load elongation curves from a typical tensile sample, they're shown here. So at low irradiation and test temperatures, you get, after the elastic regime, you get yielding and then prompt localized flow or necking in the sample at the low temperatures. And then you have, finally, when you get to high enough temperatures for the irradiation and test, then you get back to the normal work hardening type of behavior that's desirable in any structural material. So from looking at uniform elongation, you would say this material was brittle. And in the 1960s and 70s, this phenomenon in general was called radiation embrittlement. That's actually a misnomer. That's an incorrect terminology to be used, because if you look at the fracture surfaces of this specimens, so here's showing a sample which had a uniform elongation of 0.2%, so extremely low uniform elongation. But if you look at the reduction in area on that sample, it's reduced. It looks extraordinarily ductile. I mean, this looks like unirradiated material in terms of reduction in area. It has a reduction in area greater than 90%. So by one measure of ductility, it's highly ductile. By another measure, it's brittle. So what's going on with that? The leading explanation is a phenomenon called dislocation channeling, which is a form of highly localized flow in the material. So in the bottom micrograph this is a transmission electron micrograph of one of these vanadium alloys after it was irradiated at 270 degrees centigrade. So in the middle of this kind of a low uniform elongation regime, the kind of the black spots you see in the background are the defect clusters produced by that neutron irradiation. And then the sample was tensile tested, and so in this case there would have been a dislocation source operating somewhat off screen here, and the first dislocation passes through the material, and somehow absorbs defects as it's interacting with the defect clusters as it passes through there. Then the next dislocation emitted from that same source now sees a relatively clear region where it can follow right behind where the initial dislocation path was located, and you get hundreds of dislocations following all in the same path. And so as a result of that, you get extreme flow localization. That in turn gives rise to this very low uniform elongation, but high reduction in area that occurs in the material. So just to, we've then examined this in a series of materials by doing some in situ transmission electron microscopy and molecular dynamics simulation studies to understand a little bit more these phenomena that are going on. So in the right-hand picture, I'm showing dislocation line while in situ tensile testing. Here's a stacking fault tetrahedron, and the dislocation has come up upon this, and there you saw that it sliced through that defect. It essentially absorbed, as it was approaching this stacking fault tetrahedron is kind of a four-sided pyramid, and all of the tetrahedron below where the dislocation line intersected the tetrahedron were absorbed by that single dislocation and were taken out, and only the remnant or the apex remaining above the intersection with the tetrahedron remained after that. So you've taken a pretty large defect cluster, and in one swing of an axe of your dislocation, you've taken out 70% or something of the vacancies in that defect, and it's now become a much weaker obstacle. Then one can imagine a second dislocation coming along, intersecting it again at some point, again taking out the lower parts of the tetrahedron, and you're eventually left with no defects overall in that whole process. So looking at this in more detail by molecular dynamics simulations where you can really slow everything down, showing two different views for dislocation as it approaches this stacking fault tetrahedron. You can see most of the vacancies get absorbed by that single passing dislocation. Looking at it on this view, you can see quite clearly this formation of this, you get the nice jog formation, and then the jog simply glides away from that, and you're again left with that small remnant of the stacking fault tetrahedron. From the experiments that we did looking at different temperatures and so on, we wanted to understand the role of vacancies, so we went to above and below the vacancy migration temperature, etc. We found that this was one of at least three different distinct types of interactions that would occur in the material. So it's not every dislocation interacting with the stacking fault tetrahedron will follow this mechanism. There were two other types of mechanisms. One is a collapse to a loop, and the other is a complete absorption of the stacking fault tetrahedron within the dislocation line in the material. But in general, these all depend on test temperature, strain rate, and other parameters. So with this and with lots of other studies that I don't have time to talk about, I go over most of this in a semester-long class that I teach at the University of Tennessee in 45 minutes. I can't cover a semester's worth of radiation effects. We have come up as a kind of the international radiation effects community with three general strategies for designing high-performance radiation-resistant materials. And they're listed here, and then I'll go through each of these kind of in the remaining time that I've left for this lecture. So the first approach is to utilize materials that have negligible point defect mobility at the temperatures that you're going to operate at. And as a restriction for this general, because if the defects can't move and coalesce with one another, they're basically, as you go to higher and higher damage levels, you're going to get what's called cascade overlap or defect overlap type of a condition, and the defect concentration will saturate. And it actually saturates quite quickly at less than 1 dPa kind of doses. And then going from 1 dPa to 100 dPa, essentially nothing else will happen to the material. So it ends up giving potentially very good radiation resistance. A restriction for this is that in many materials, the disordering associated with irradiation in the regime where you have no defects being mobile can lead to amorphization in the material. So in general, for many materials of interest, it's actually better to select a temperature range where just one of the two types of defects, the vacancies, are immobile, and you can let the interstitials be mobile. So if the vacancies are immobile, they get continuously created, end up producing a very high so-called sink strength built into the material by the irradiation, and the interstitials migrate around and they'll quickly find a vacancy and recombine. And so all of the interstitials will get recombined, and you'll get very good self-healing from that process. The second approach is to use materials that have intrinsic resistance to radiation damage. And the best known case of this is over the years is body-centered cubic structures, alloys. But there's many other categories that will potentially could fall into this, and I'll show some examples for BCC alloys as well as high entropy alloys, and potentially bulk metallic glasses as a third possibility that would fall into this category. And the final approach is to use materials that have a very high density of nanoscale recombination centers, either in the form of precipitates or dispersoids. It could be nano-layered structures, a number of other features, and I'll show a few examples of that in a couple of minutes. So going to the first one on this list, which is if we let the vacancies be immobile and let interstitials be mobile. So I plotted here the temperature range for a bunch of different materials in the periodic table with red bars. The lower extent of the red bar is the onset temperature for interstitial migration. The upper extent of the red bar is the onset temperature for vacancy migration. So anywhere between the lower and upper region of this red bar, all of these materials are going to have extremely good radiation resistance in general, because they're just going to, the interstitials will all recombine with the vacancies that are being produced. So that, looks fine until you start putting on what temperatures you might want to use these materials at. So copper, if you wanted to design something for dry ice temperatures, copper would be a great choice. If you want to design a material for a light water reactor, core internal, or for a generation 4 sodium fast reactor, or one of the other concepts, essentially all of the metals don't work. I mean, this concept is academically quite interesting, but it just doesn't work. Possibly tungsten is one case where it could work for a light water reactor core internal application. But out of this set of materials, one that in particular that jumps out as being intriguing is silicon carbide. And it has an incredibly large difference in temperatures between the onset temperature for interstitial motion and the onset temperature for vacancy motion in the material. So over this very wide temperature range, it should have very good radiation resistance. And that includes a lot of reactor relevant types of temperatures. So what happens if you look at the radiation behavior of silicon carbide in terms of its dimensional stability is shown in this plot. So this is the amount of volumetric swelling as a function of irradiation temperature. At very low temperatures, below the onset temperature for interstitial motion, it undergoes this crystalline to amorphous phase transition, swells about 10% after a fraction of a dPa. The properties are very poor, so you wouldn't want to use silicon carbide at room temperature. It would have very poor radiation resistance. Similarly, at very high temperatures, above the onset temperature for vacancy motion, you start to go into the void swelling regime because vacancies are mobile and can collect together. And as you go to higher and higher doses, the amount of volumetric swelling just keeps increasing and increasing. So at high temperatures, silicon carbide is a poor radiation resistant material. However, in between those two limits, it has, which is onset for interstitial migration, onset for vacancy migration, it has extremely good radiation tolerance. So we're plotting here the amount of volumetric swelling as a function of a radiation temperature, and there's a number of different doses of data shown here that the increase in the swelling occurs after about 1/10 of a dPa up to 1 dPa, and then essentially saturates. And then I've shown here a star point after 40 dPa. There's now 70 dPa data that fall right on top of that 40 dPa results. Within the next year, the 100 dPa data are just coming out of reactor after 10 years of irradiation or something. And we fully expect that they're going to fall right on top of these other points. So you can have a very stable type of a microstructure if it's irradiated at these intermediate types of temperatures. But silicon carbide in general is not a radiation resistant material. It's radiation resistant for this one special temperature regime where vacancies are immobile. So the second general category is to utilize matrix phases that have intrinsic improved resistance to defect accumulation. So I've mentioned before, body-centered cubic materials are an example of that. And just to demonstrate that, I'm showing here some neutron irradiated weld metal, type 308 stainless steel, that has a face-centered cubic or austenitic matrix, and then it has body-centered cubic delta ferrite stringers produced in that weld metal. So this material was then exposed to exactly the same neutrons at exactly the same temperature. Here's the microstructures taken from the delta ferrite, the BCC phase, and here's the microstructure, same neutron, same temperature, in the face-centered cubic phase. If you sum up the number of defects that are visible in these two cases, it's about a factor of 30 lower total visible defect accumulation in the body-centered cubic phase compared to the face-centered cubic phase. Similarly, if you look at results for volumetric void swelling that various researchers have obtained over the years, the results for several different types of face-centered cubic materials are shown that after some initial transient dose, you go into a rapid high swelling regime, whereas the body-centered cubic steels up to 200 dPa are showing quite low volumetric void swelling compared to the face-centered cubic types of structures. So there's many other potential categories of materials that go beyond just face-centered cubic versus body-centered cubic. So one example that we're recently starting to explore are looking at high entropy alloys. So first, if we look at conventional iron, chrome, nickel, or iron, chrome, manganese face-centered cubic alloys, this is a plot just showing near grain boundaries what happens to the solute concentration. We find depletion of chromium and manganese near the grain boundaries, and we find enrichment of nickel next to the grain boundaries in that region. We've made a high entropy alloy, which is a material containing equal atomic concentrations of 4 or more elements. In this case, iron, chrome, manganese, and nickel, each at about 25%. And when we irradiated this material, we found that it had completely different solute diffusivity results compared to the conventional. So they're both face-centered cubic materials, both containing the same types of alloys. You just change the relative concentrations of each of these to produce what's called a high entropy alloy. You get with high entropy alloys, I should say, you get a high configurational entropy if you have nearly equal atomic concentrations. And so the free energy if you have nearly equal atomic concentrations in a alloy containing 4 or more solute elements, that can be the dominant contribution to the total free energy. Whereas in usual cases, we think only of entropy or enthalpy as being the dominant contributor. In high entropy alloys, the entropy term, the T delta S term, can be dominant. And so once you switch from being enthalpy controlled to T delta S controlled, that could mean lots of other things can change as well. And so what we found in this material, looking next to the grain boundary, instead of getting chrome and manganese depletion, we found enrichment, that it completely flipped sign, and we found nickel depletion in the material. So there's explanations for this by kind of classical understanding of radiation-induced solute segregation theory. There's what's called the inverse Kirkendall vacancy mechanism, interstitial solute drag mechanisms, etc. And generally, there's a ratio of the diffusivities of A and B solutes by vacancy mechanisms and interstitial mechanisms, that if that ratio is greater than 0, then you're going to get depletion of the solute, etc. So what these results suggest is that we've completely flipped these ratios of these terms. And moreover, looking at the microstructures of these, the overall diffusivity has been greatly reduced in these materials. So this particular alloy is not the ideal radiation-resistant material, but it suggests that by exploring concepts like high entropy alloys, there's a whole new field of alloys or materials out there that potentially could have be tailor-made to have very high resistance to radiation. Then the final category is take away the crystalline structure completely in terms of possible radiation-resistant matrices. And so going to a non-crystalline type of a structure is the right approach. Unfortunately, if you just take off-the-shelf types of materials, their response to radiation can vary. In some cases, as you start irradiating the material, you can get significant volumetric expansion, and that can lead to cracking and so forth in the amorphous material. You can get contraction or densification in the material. And in some cases, you can get it to stay quite stable, which is the desired type of an approach. And understanding this requires a lot of sophisticated microstructural analysis, because in both of these cases, these are long-range structurally disordered, but this one has a different short-range ordered state compared to its initial state. So we're now doing some detailed studies of looking at the pre-irradiation and irradiation study of different bulk metallic glasses and quantifying the short-range ordered states in these materials, and then from that being able to try to build up knowledge that will be able to design materials that will show this very good overall stability. So one of the initial materials that we've looked at in terms of its hardness and elastic modulus and so forth, we're finding a slight change at low doses, and then it seems to be remaining quite stable, going out to at least 10 dPa in some of our early ion beam irradiation types of studies. Then the final, the third category for designing in radiation resistance is utilizing what's called as a high sink strength. And this technique, you can imagine, you've created mobile interstitials and vacancies in the material. If you could introduce some defect recombination centers, just think of them as like a parking lot or something like that, or a skating rink, where at some point in time a vacancy would hop into this parking lot, and then sometime later an interstitial, and it doesn't get released from that parking lot. And sometimes later the interstitial comes along and it also hops into that parking lot, and then they're being locally combined or confined in this region. The vacancy and interstitial will eventually recombine with one another. And that's the general concept for this, for coming up with the high sink strength types of materials that has proven over the years to be a very effective way to get high radiation resistance. So here is a plot of volumetric void swelling versus a parameter that's called the sink strength, which is just a way to quantify the density and the size of these recombination precipitates or other defects, sinks in the material. And you can see the rapid decrease in the amount of void swelling as you increase the sink strength. And then once it gets above a unit of about 10 to the 15th per square meter, then you have a very low overall amount of void swelling. And it continues to get better as you go to higher and higher sink strengths. More recently, we've discovered that this same effect may also reduce the amount of radiation hardening and embrittlement in the material. But in this case, you have to go to about an order of magnitude higher sink strength than previously, up to 10 to the 16th per square meter. And then you get a reduction in the amount of radiation hardening that occurs in these materials. This has only, these experimental observations have only come about with studies that have been done on the so-called oxide dispersion strengthened steels, which are new materials that go to these ultra-high sink strengths compared to conventional kinds of steels, which are typically only in the 10 to the 14th to 10 to the 15th kind of a sink strength. So this has spurred a lot of interest in the so-called ODS steels or other ways to make steels and other structural materials with ultra-high sink strengths that may also reduce the amount of radiation hardening and embrittlement. And again, the process for the recombination is if you have, this is an example, high resolution image of an ODS, oxide dispersion strengthened particle, but a defect that's migrating through will come in and be trapped along the surface of this particle, and then a little bit later in time, a vacancy can come along, and this just acts as a collection center for the defect and anti-defect to show up, and then as they're migrating around that surface, they'll eventually find each other and recombine. There's many other ways that one can imagine coming up with these very high sink strengths. So there's work at Los Alamos and other places performed over the last few years looking at nano-layered structures that introduced very high densities of interfaces, and that proved to be, in certain cases, very effective ways to cause point defect recombination. Another way that we're looking into is a way to make bulk nanostructured materials, so-called max phase ceramics, which are layers of ceramic, TIC in this case for the Ti5Al2C3 max phase, separated by an atomic layer of metal, aluminum in this case, and then a couple layers of titanium carbide, then another layer of aluminum, etc., etc. So one can imagine that these interfaces might end up being possible good recombination centers that are just built in by the thermal processing as you make this bulk max phase ceramic material. So we've been performing some irradiation studies. Here shows a result after up to about 10 dPa at 400 degrees centigrade. We're seeing some slight modification of the structure, but more or less retaining the layers. We had concerns that we might get severe mixing between these layers and lose completely this type of structure, but this appears to be holding together reasonably well, and so now we're exploring over a range of temperatures and doses to see, ultimately what's the overall stability of these types of in situ nanolayer types of structures. So in the last couple of minutes, I'll just quickly go through how we can use some emerging or current available material science techniques to try to develop high performance materials. I'm showing in the left plot the historical record for coming up with steels with ever increasing upper use temperature as a function of date that the steel was introduced. You get this nice linear relationship. Unfortunately, the slope of this is only 2.5 degrees centigrade per year, so we're steady and slow in our progress. If you look at the overall variability of some of the current heats of commercially available materials that are out there, it's pretty pitiful. You can have an order of magnitude variability in the thermal creep strength of nickel-based alloys that are out there. These are all within the ASME spec in terms of composition, but you might get, heat 1 behavior, you might get heat 3, so we have to over-design material, make them too thick, if you will, design for the worst performing case in order to account that we don't get any failure in these materials. And so there's, with the great improvements in computational thermodynamics over the last decade, particularly the databases going into this, we now, there's no reason that we shouldn't be designing all of our steels and other high performance structural materials using computational thermodynamics. And so we can use this to tweak the current compositional specs to give them the correct specification and to design new high performance alloys. And so you would think that after all these decades that all of this has been experimentally studied, and it's actually not even close. So even as you go, so for binary alloys, we've done a reasonable job of exploring the periodic table. But even if you go to ternaries, only about 10% of the possible ternary phase compositions have ever been experimentally investigated. It's 90% we haven't even looked at. And steels are you're usually made of like 8 compositions. So how many steels have we really sorted out the whole composition? This is just showing one simple example from computational thermodynamics for 2 different compositions of a precipitation hardened steel with very slight differences in the composition. Both are within the allowable specification for this steel. You could buy this steel today off the internet. You could buy this steel today off the internet. And both are fully legal and authorized. For precipitation hardened steel, you want to solutionize in a single phase region, and then you come back and give it an H treatment at a second temperature to precipitate out the desired phase, in this case M23C6. This one will give you spectacular properties if you use this composition. This composition over here, if you heat solutionize, you're going to have about 10% ferrite, which is an embrittling phase occurring, and then you come back and you give it the aging treatment, and you're going to get additional ferrite, but you're also going and you're going to get the M23C6 that you want, but you're also going to get chi phase, which is another embrittling phase. This is going to be a disaster. But again, they're both allowed, and the difference in the composition is minuscule. It's 1% difference in the chromium level, 0.5% in molybdenum, and 0.25% in nickel makes all the difference in these 2 compositions. And again, for typical steels, if you have 8 compositions, if you were Thomas Edison and you tried to just make these heats, and you made a matrix with 4 different solute compositions for each element, that would be about 1 million heats just to investigate one alloy experimentally. Nobody's ever done that. But you can do this on a computer with computational thermodynamics in 2 or 3 days. You just write the script, let it run, and it will trace out the entire phase diagrams. We've done this, some of my colleagues at Oak Ridge have done this with the 9 chrome 1 moly steel that was originally developed at Oak Ridge in the 1980s, and they discovered this composition is wrong. And aging studies that have been going on, this is an alloy that's used worldwide, it's $1 billion per year kind of an alloy, are now showing phase instabilities after 30, 40 years of operation. And by the computer, we know it's wrong, and we know how to fix it. It's only a matter of moving the composition by about 0.25% in a couple of key elements, and you would be back to having a very high performance material. So this is an old example of Ron Klee, who worked at Oak Ridge, then tried to apply the computational thermodynamics to two existing commercial steels, a 9 chrome 1 moly and a 12 chrome steel. He recognized by playing around with the computational thermodynamics that if he added a hot rolling step where he controlled the temperature during the hot rolling, the dislocations produced by that hot rolling step would nucleate precipitates. And so when he added that step, he increased the precipitate density by about 1,000 times from that material. No change in the composition. That's, you know, we could have gotten a further improvement by tweaking the composition. So some other examples from lesion tan, more recently, just making some slight tweaks in the composition, made 3 so-called reduced activation heats of steel that are about 60% stronger than the existing 9 chrome class of steels that are commercially available in the material, with no reduction in ductility. So 60% stronger without any change in any other properties. And then finally, where we're going with this also is introducing advanced manufacturing techniques. So here's a result of some things from a DARPA challenge on additive manufacturing. That this was all made by just CAD drawings and very rapidly being able to produce unique types of structures in the material. What's not evident from this is the buried hydraulic lines that are in here, that you could not produce this type of a structure. I mean, it's simulating vanes and so forth that you get hydraulic actuators. You could not make this by conventional techniques. And so this geometric complexity is now easily possible by advanced additive manufacturing types of techniques. Being able to scale this up to larger sizes. So Oak Ridge last fall made the first large-scale car by additive manufacturing. I think it printed in 24 hours. This is a Shelby Cobra at the January North America Auto Show. They printed this car in, I think it was 48 hours. And so, I mean, the total team, this is made out of 20% carbon fiber reinforced high ballistic grade plastic. The weight reduction of this car is about 50% compared to the 50-year-old, the original classic Shelby Cobra. And it's 3 times as strong as the original car. If various teams like to make these old cars, there was an article that estimated that the time it would take a team to reproduce one of these classic cars by traditional techniques, it was going to be a dozen people working for a year, I think, to build this up from scratch. This was, I think, 5 people. Total time from starter project to end was 6 weeks. And the print time, again, was a day and a half or something like that. So there's, I think with additive manufacturing, there's potential to get significant improvements in the performance of the material along with the geometric complexity while maintaining reasonable costs of the material. Usually as you start to make real world types of materials, you get some degradation as you start to weld the material and as you start to do other fabrication techniques. You tend to get degradation in the performance, but there's possibilities with things like additive manufacturing that you're being able to not sacrifice a lot of the traditional loss of performance that occurs by the conventional techniques. So with that, thank you for your attention. And again, this is just a quick summary of things that I've already covered. Thank you.
So any quick question for Steve? Ed?
You used every word that you use in a materials course except one, and that's cracking. And when you are moving towards these things like tungsten and silicon carbide, isn't that a consideration? And how does that paint into your overall picture?
Yeah, so the silicon carbide, you engineer in crack deflection interface into the material. So I completely glossed over that, but the silicon carbide composites are the key. That bulk silicon carbide, you would have the cracking problem because it's a brittle ceramic. But by engineering in crack deflection points in a silicon carbide continuous fiber reinforced composite, you can have fracture toughnesses that are approaching the fracture toughness of the wings of the airplane that I flew out on yesterday. It's reasonable fracture toughness values can be engineered into an inherently brittle material by adding those crack deflection and blunting points. You could do the same thing with tungsten. We're looking at tungsten fiber reinforced composites. Tungsten by itself, very low toughness and ductility. The future for it is also very analogous to the ceramic matrix composites, coming up with a cost-effective route for tungsten fiber reinforced tungsten matrix composites, and then it would be a great potential material.
Quick question. For the max phase material, the titanium aluminum carbide, have you measured the change in the electrical conductivity as a function of radiation damage?
We will be. This was some ion radiated results that I showed that it's difficult to make an accurate measurement of the conductivity, but we also have neutron radiated samples that have just come out of the reactor that in a couple of months we'll be measuring. So I don't know the answer yet.
Thanks.
Yeah, quick questions? Just Steve is going to be around for a little bit. If anybody else has some questions, you can have a discussion.
I have an announcement.
Oh.
The American Nuclear Society meeting will be having today. Rob Beamler from the U.S. Army. He will be giving a talk on counterproliferation and weapons of mass destruction. That's at 6 o'clock down the hall. There'll be pizza, stuff like that.